Hello everyone, I'm Lawrence from Extrapy. Welcome to Module 4 of our Cairo auditing course. And in this module we'll be looking at the structure of Cairo contracts. We'll start off with looking generally at the anatomy of the contracts, and we'll have a simple example to show you those details. Then we'll look at contract storage. We'll then look at some more advanced features such as components. We'll see how we can include OpenZeppelin contracts within our contracts, how to interact with other contracts, and we'll finish off having a quick look at build tools. So, features of a contract, well, they consist of storage and functions. They can interact with other contracts, and composability is a key design feature for blockchains. We see this particularly in decentralized finance applications. Contracts are permissionless, and so this means that the access control that we want to have in our contract must be explicitly added by the developer. Of course, when we're looking at the security of the contract, when we're auditing the contract, looking at access control is going to be a vital part of that. You also need to remember that Starknet contracts are transparent. This means that there is no privacy on Starknet. Any data within the contract can be viewed by anyone. So what are the differences then between a Cairo contract and a Cairo program? Well, you can think of the contracts as being programs that are deployed on Starknet and run by the sequencer. But the fact that they are on Starknet and they're interacting with the sequencer means they have access to the state of Starknet. Contracts do not have a main function as programs do, but we can have multiple entry points into the contract, via external functions. We define our contracts within modules, and to indicate which parts of the contracts are which, we use annotations. So, for example, we want to show what part of the contract is storage, and we have an annotation for that. Or if we want to describe how functions work, then we have an annotation for that. We need to tell the compiler that what we are writing is a contract as opposed to a program, and so for that we have this particular attribute here, the Starknet contract attribute. So what's the basic anatomy that you're going to see in a contract? Well, as I say, we need to have the Starknet contract attribute there to tell the compiler that we are declaring this code to be a contract. So you could see something like this. The module here is where we will have our code for our contract, and we have our contract name there. Where we want to use storage, we use the storage attribute. So you can see we have a struct for that called storage, and then we give that the storage attribute to show that that is storage. We can also have a constructor. So this is something that we can use to initialize the state of our contract. And so you can see the constructor attribute there being added to a function. So that function will run when the contract is deployed. If we want functions to be external, if we want them to be available to be called from some external source, such as a DApp, then we should mark them as such, as you can see there with that attribute. And then we can also declare events, and so there's an attribute for that, and you can see there that we're defining an event. Okay, so let's have a look at functions in a little bit more detail. So, as with other blockchains, we have the concept of read-only functions and read-write functions. Now, the signature of read-only functions is that they have a snapshot as one of the arguments. So you can see here we've got this function signature get total. The argument for that is a snapshot. So the there is showing that it's a snapshot of the contract state, and then we're putting that in a variable self, and then that is going to return a U128. So within the body of the contract, when we come to implement this, we would use that self variable to read some of the contract state. If we want to be able to write in our functions, if we want to be able to update state, then we need a reference to the contract state. And so you can see the different arguments here. The first argument here is a ref to the contract state. And again, we're putting this in the variable self. And then the second argument is the argument that is representing the business logic. This is some update that we're going to want to do. So we're going to want to specify an amount that we're going to need to add to our contract state. Now, a very common practice when you're writing programs or contracts is to create an interface to show the behavior of that contract and to list out the functions that contract is going to implement. And so to do that, we have an interface attribute. And so here you can see that being applied to a trait. And this is parameterized with the T contract state to show that this is going to be a trait to represent a contract. And so within this trait, we could then list out the functions that our contract is going to implement. So let's put all of that together and have a look at a very simple contract. This is from the Cairo book. There's a link to that there, so you can look for further details in that. So first of all, we declare an interface. So this is going to be the interface to the contract. So it's declared as a trait. We're going to call this iSimpleStorage, as standard sort of naming convention there. And as I said, it's parameterized by the T contract state. We have a couple of functions that we're going to implement in our contract. So we have a set and a get. And the signatures of these are typical of a read-only function and a read-write function. So our set is a read-write function, so that takes a reference to the contract state and then some value that is going to be used to update that state. And then the get function takes a snapshot to the contract state and is going to return a value U128 from the function. So that's the interface. So when we want to create our contract, we use an attribute to show that it's a contract. We declare this as a module, and we have the name of the contract there. So it's a simple storage, and then the interface is iSimpleStorage. It's the kind of the convention tends to be used. We can use other modules. We can bring in other modules. So here we need to use a module for this storage. So we've got the use keyword here for that. And then we define the storage for our contract. So within the struct, we're going to define all the fields that we are going to have in storage. So in this case, we've just got one field called stored data. And then we have the storage attribute on that struct to show that is where we're declaring storage. And then we now provide an implementation of the interface that we defined earlier. And so you can see here we use the import keyword for that, and we show that that's for this simple storage contract. So we're implementing simple storage of the iSimpleStorage that we defined as our interface. And then because this is the implementation, we have to provide the implementation of the function bodies. So we have the set function here, where this is receiving a reference to the contract state, and we use that. Gives us the self variable, and then we can use the dot syntax here to get the relevant field from the storage. In this case, there's only one, but obviously there could be more than one. So we can use self.stored data that specifies this particular field, and then to change that, we can use the write method, and then we pass in the argument to that, which is the x value that was passed into our function. For the read-only function, again, we have a self variable. This time it's representing a snapshot, and the snapshot of the contract state. And then we can use that again with dot syntax to refer to an item in storage. So we have dot stored data. And then this time we use the read method to read that value. And then that is the value that gets returned from the function. Okay. So storage, as we saw, this is where we hold the state of our contract. We need the attribute storage to indicate that that's what is where we're holding it. And so you can see an example here. We've got a couple of fields for this example in this struct. So we've got a total, a U128. We've also got here a reference to an external contract. So maybe we're storing that because we're going to want to interact with an external contract later. Okay. So some more advanced features, we can also have components within our contract. And so to declare those, we have this particular attribute, and you can see that being applied to a module there to show that it's a component. We also can use the generate trait attribute to give us an implementation of a trait that we have. So you can see there that we've got some trait internal contract, and then we are using the impl keyword to get a implementation of that trait. Okay, so going on, OpenZeppelin contracts. I'm sure you're aware OpenZeppelin provide implementations of Solidity contracts for common patterns. They also provide Cairo implementations for common patterns. To use these, we simply need to add a dependency to our config file. So you can see the dependency there. The latest version is 15.1. So if you have that, then you can use those contracts within your contract. You can import those. If you want to see what one of the OpenZeppelin contracts looks like, then there is a link there to an example of an ERC20 contract. Now, I mentioned components earlier, that we may want to declare these. These are a way that we can make our code more modular. For example, if we have some functionality that is common to a number of contracts, it makes sense to create that as a component and then allow that component to be used in the contracts. And that component can contain storage or events or functions. But unlike a contract, we can't deploy this component by itself. It has to be done as part of a contract. So what does that look like if we want to create one of these? Well, again, what we do is we start off with an interface. So we declare a trait. And again, we're saying that this is parameterized by contract state. And within this, we decided we're going to have a certain function called owner. So this whole component is about ownership. So this function is taking a snapshot of contract state, assigning that to a variable, and is going to return us an address. And then the declaration of the component itself, we need the component attribute here, and then we can use that on the module for our definition of the component. We want to import some items, some functions from Starknet, so we can do that. We want to have some storage within our component, so we can declare that. So we have our storage struct here. It has one field, which is owner, and that is of type contract address. And then we are going to provide the implementation of the trait. So we use the impl keyword, and this is then going to provide the implementation of our owner function. So you can see there we can write our owner function and have the function body. So the signature we've already spoken about, and then the actual implementation is quite simple. It takes the snapshot, which is assigned to the self variable, uses the dot syntax to get the owner field, and then it calls the read method on that to read that value, read the contract address that is the owner, and then it can return that from the function. Okay. So we will probably want to interact with other contracts. There's a link there to some documentation about that. In order to do this, we will need to know the interface of the contract we want to interact with. And so the interface is a list of the functions that are exposed publicly by that contract. So it's providing the function signatures that we are going to need. And for as an example, we've got what's a ERC20 interface would look like. So these should look familiar to you. This is following the ERC20 standard, and we're also able to create an ABI, which is a JSON representation of this interface. So this means that this is something that we can use within a front end, for example, and it allows then the front end to know how to call functions within the contract. Now, when we create an interface for the contract, the compiler will create dispatchers for us. And so if you imagine we've got an interface called ERC20, so this could be the interface for the ERC20 contract, then we would have a contract dispatcher, the ERC20 dispatcher, or if it's a library, we would have the ERC20 library dispatcher. And this also the compiler will also give us a trait, which allows us to call the functions for the dispatcher. So if we imagine that we're going to call a contract which has an interface which defines two functions. These two functions are name and transfer. The way that we could do that would be to write our contract. Now, I haven't given you the interface for this contract here, but you could create that in the normal way. But then within the definition of the contract itself, we have the contract attribute to tell the compiler this is a contract. We've got the name of the contract there. We've got some imports that we are going to need. We've got storage being declared, although we're not actually using anything within that. And then we have the implementation part of our contract. So this is where we are going to be writing our functions. And in this case, what our contract is a wrapper. We're wrapping it around a token. So we're taking in a function call, and then dispatching this off to another contract, and then returning the result from that. So the first function we've got here, token name, it has a variable self, and it takes a snapshot of contract state. We also need the contract address that we are wrapping around, and this is going to return us a felt, which is going to represent the name of the contract. And then to do the actual call to the other contract, we use the dispatcher that has been created for us. We give that the contract address that we want to call, and then we can use the dot syntax to specify the function within that contract that we want to call. So in this case, we've said there's a function called name, and so we can use the dot syntax to call the name function, and that will bring back the name of the token in this case. And then if we have an example where we want to update the state, we could have a transfer. So you can see with this, we need a reference to contract state. We need to, again, pass in the contract address we're going to interact with. And then the other arguments we usually need with a transfer are the recipient and the amount that we're going to transfer. So we need all of these to be passed into our function. And this is going to return as a bool to indicate that the transfer was a success. And then we do a similar thing again. We use the dispatcher, we pass that the contract address, and then we can use the dot syntax here to specify the function that we're going to be calling, and we pass to that function the recipient and the amount. So the transfer function is the function in the contract we are wrapping around, and we call that in the normal way, and then we will get back from that a Boolean, which we can then return from our function. So I'll just end with talking about build tools. The common one that we use is Scarb, which really is equivalent to Cargo in Rust, and this will manage dependencies for you and allow you to build your project and to test it. There's a link there to a cheat sheet so that you can see all of the commands. We now also have a Starknet Foundry, which is a based on Foundry. If you're familiar with Foundry from Solidity, it's based on that, but it allows us to write Cairo contracts as well. And we've got a link there to documentation for that. Okay, so that's a few details then about Cairo contracts and what they look like. This is going to be useful for you when you are looking at the contracts, inspecting the code. I hope that this gives you an idea of what the different parts of the contracts are trying to do, and so will help you when you're trying to do your audit. Okay, so that's the end of Module 4. I look forward to speaking to you for Module 5. Thanks, everyone.